Up until this point in higher and National 5 level materials, we've been plotting straight lines, and we've been plotting them on a standard set of axes, so your x and your y axis, or depending on the variables that you're using, possibly something like a P and an M, profit and money. What we're going to start to look at is what happens if we've got a relationship between two things that increases exponentially to the point where your graph's going to shoot off to infinity and you're not going to be able to include enough data in that graph. It's not going to look anywhere near as good as it could, and you're not going to be able to read or interpret it as much as you would want. So what do we do when it comes to that? Well, what we're going to do is we're going to look today at plotting on logarithmic axes. We're going to look at justifying that by plotting on these. And we're going to start by looking at equations of this form here. Y equals AB to the power of x, where A and B are constants, and x, the power, that's our dependent variable. That's the thing that changes the overall value and worth of our equation and takes it on from there. Now this is what we're going to look at here now. When we're doing this, what we're going to have to do is then change the axes and how we express them. We can no longer do it in y and x. We're going to do them exponentially. Again, the good thing about this is it allows us to accommodate this hugely changing set of variables. So for example, if you wanted to do a plot of time versus population, well, if that was on a standard x and y axis, something along the lines of this, what you would probably find is that you'd get an OK set here, and then all of a sudden it would shoot. You would have to make your graph absolutely massive to accommodate this. So logarithmic axes will help us to accommodate this by taking up just as much room as a graph like this would have. Now, in order to do it, we have to understand what it looks like. So let's imagine we plot it normally, something of the form y equals AB to the power of x. A and B are both bigger than 0. This is your standard plot here. Cuts the y-axis at A, doesn't go below 0 in the y-axis, looks like this. What we can start by doing is taking logs of both sides. So if we take log to the base e of y, and log to the base e of the other side of the graph as well, AB to the power of x, what we're able to do is use our rules of logarithms we covered previously to manipulate this side here on the right. So what I'd be able to do is take that and say it's log to the base e of a plus log to the base e of b to the power of x. Now our x, our dependent variable, is still a power here. However, I can use my other powers of logarithms to bring it down to the front. And what I'm then able to say is log to the base e of y equals log to the base e of b, putting that in a bracket because that's then multiplying the x, plus log to the base e of a. Now this almost has a form that we've seen in the past. If you think back to straight lines, we know the formula for a straight line is y equals mx plus c. This has a form exactly like that. What we can do to kind of manipulate it and get it a bit better than that is what we're able to state is we have a capital Y and we let that equal log to the base e of y. I can rewrite my equation to be big Y equals log to the base e of b times x plus log to the base e of a. So what I now have is I have this in the form of a straight line where y equals log to the base e of y. This here is what's called a logarithmic axis. This will plot a straight line relating the two of them on a set of axes where one of them increases exponentially to accommodate the change in data. And it's actually quite interesting to see. It would look something like this, where big Y, my log to the base e of y, would be the up and down, the y-axis, and my x-axis going along would be simply the variable x. There's been no change in terms of logarithms to that. And it would give me a straight line. Now, our x variable would go up constantly, so this would maybe go up in ones going along here, so 1, 2, 3. However, our y wouldn't. Our y could change exponentially. So this here could maybe go from 1 to 2. The same jump would then maybe go from 1 to 5, then 5 to 10, and so on and so forth to accommodate the data. It all depends on the form of the logarithm we have. Now, as I've said, that's of a form y equals mx plus c. From that, we can read off two key properties of the graph. We know our y-intercept is going to be equal to log to the base e of a. That's this value here, my y-intercept. That's going to be log to the base e of a, whatever that value is. And I can also read off the gradient of my line as being log to the base e of b. I can get the gradient by simply taking those. Doing that, I can then express it in this form. solve that equation and get back to my equation of the form y equals ab to the power of x. Now, there's a lot of information to throw at you and a lot to see with just logs and y's and x's kicking about everywhere. The best way to show it is with an example. So let's imagine I've got an experiment and I've taken the experiment and it's tested the relationship between two variables and they're found to be in the form that we're looking at, y equals ab to the x. That's the relationship we can get. The graph is plotted below on a logarithmic axis and I want to find a and b. So here's the graph. This is what it looks like in a logarithmic axis. And I've got a couple of key bits of information. Now I know y equals ab to the power of x. To manipulate it and get it in the form we want to take our log to the base e of both sides again. Log to the base e of y equals log to the base e of ab to the x. And I can then manipulate this side again using my rules of logarithms. Doing that, I get log to the base e of y equals my log to the base e of b again, times x, plus log to the base e of a. So I've now got both of those parts here. Now from this, I can then make big Y equal to log to the base e of b times x plus log to the base e of a. So what I've now done is manipulated it, turned it into a straight line on a logarithmic set of axes, so I can now equate it and the information to this. I can now start looking at it like that. Well, remember y equals mx plus c was the form of a straight line. C relates to that, m relates to that. Now I know c is my y-intercept, which in this case is 3. So from that I can simply say that log to the base e of a equals 3. And again we can manipulate this using the rules of logarithms. Remember, when we did rules of logarithms, log to the base n of y equals x could be changed to being y equals n to the power of x. I can use that for this one and state that a equals my base, which is e to the power of 3. So there you go, I've got a value for it. If I plugged it into a calculator, I'd get some sort of numerical value out for it, and I would answer my solution for that part. What I now want is log to the base b of e. Well, I know log to the base e of b equals my gradient, and we know what the form of the gradient of a straight line is. It's our y2 minus y1 over x2 minus x1. We only need 2 points for it. Well, I've got 2 points. I've got this here, my first point there, and I know my y-intercept. Remember, the x-coordinate of the y-intercept is always 0. So we can just plug that information in. So it's going to be 5 take away 3 over 7 take away 0. Once I've done that, 5 take away 3 over 7 take away 0, I end up getting 2 over 7. So what I can then say is, fine, I know log to the base e of b equals 2/7, and I can use the same rule up here to manipulate that and say that b equals e to the power of 2 over 7. I've got my a and my b for my equation here. If it asked me to express it as a function, I could substitute them both in and use rules to manipulate and simplify it and get something out that is of that form. It is a lot more straightforward than it looks. It's just a little bit of algebra. That's what comes into play here. Let's look at another example. Let's imagine I give you a set of data this time rather than a graph. Here's results from an experiment relating two things. One is x and one is log to the base y. Log to the base e of y, sorry. And these are the results we got for both of them. Now the relationship, again, I'm telling you is in the form y equals ab to the power of x. I want to find a and b, and then I want to state an equation for y. Now again, we have to start by taking our y equals abx and manipulating it into a straight line form. Remember, a table like this relating two variables can be used to plot a straight line, and that's what we need it to be. So we take our log to the base e of both sides, so I've got log to the base e of y equals log to the base e of abx, and I can manipulate them again. Manipulate them and I get log to the base e of y equals log to the base e of b times my x plus log to the base e of a. So I've got my two different parts there. First thing we want to do is start to find both these variables. Now I know that this here relates to my gradient again, and this here relates to my y-intercept. Well, unfortunately, I can't read the y-intercept off this time, so I have to start with the gradient. So I have to start using 2 points to get the gradient. So I'm going to pick these 2 points here. I'm going to take u as 0.1, and this one here is 0.2, but it doesn't matter which 2 points you use. You can use any two of them. I'm going to plug it all in, so y2 minus y1 over x2 minus x1, so I get 2.56, take away 2.04, divided by 2.00 to equal 1.30. Take the two of them, manipulate it and plug it in a calculator, and I get 0.73 to 2 decimal places. That there's my gradient of my line. So I've got my gradient. Therefore I can say log to the base e of b equals 0.73. My b equals e to the power of 0.73, and this time it's worth calculating it. I get 2.08. I can then start to use this to find my log to the base a. So I've got to set up my original equation again. So I've got log to the base e of y equals my gradient, which is the log to the base e of b, so 0.73 times x plus my log to the base e of a. Now at this point, I've got any point along here I can take and manipulate it and plug it in. I could pick absolutely any one. Let's start with the easiest and the lowest, 1.30 and 2.04. So I plug these values in, and then I can manipulate it and find log to the base a. Now, that means 2.04 equals 0.73 times my x, which is 1.30, plus log to the base e of a. Now, key thing to note here is it's not log to the base e of 2.04. Remember, log to the base e of y is the 2.04, so it's the whole part of that that gets replaced by it, not just a little bit. That's a common mistake you see quite often in this. I can then manipulate this and work it around, and I find that log to the base e of a equals 1.09. Once I've calculated that, stick the e up, and I get a equals e to the power of 1.09, which when I calculate it gives me 2.97. So I've got my a and I've got my b. I can now plug them into this equation here. So I know that y equals ab, so my a is 2.97 times b, which is 2.08, to the power of x. Now I have to leave it like this. I can't combine these two. They're not the same base parts, like when we had a to the n times a to the m. A had to be the same. They're not. We can't combine it, so it has to be left in this form. There is my equation written as it is. So it's a good chunk of work. However, it's the same style every time. We manipulate our equation to get it relating the two variables as a straight line in terms of logarithmic axes. We can then use the information here and relating it across to our general form, our y equals mx plus c of a straight line. We're able to figure out y-intercept, gradient, and calculate the two different parts from that. Once we've done that, we can manipulate it and find our variables and ultimately our equation if it asks. I'm going to leave you with this one as one for you to have a crack at. Here's two variables linked by a set of log axes. So log to the base 10 of y versus x. There's my straight line there. My y-intercept is at 2.1. Here's a point here, 4, 1.5. The two are related by the equation y equals ab to the x. I'm telling you that. Got two parts for you to do. Find a and b, and then write the equation in terms of y. So write the equation for y in terms of that. Good luck.